Thank you. So good afternoon. Can you hear me? Yeah, great. So today I begin the course on deformations. And as Alessandro said, it will be split in two parts. And in the first part, the first three lectures, the one that I cover, I will mostly introduce to you the idea of conformal perturbation theory. And this is something that captures an operation that you can do to your conformal theories. And it's the operation of deforming it by some operators in order to construct a new quantum field theory. And actually, what I will do will be even more specialized. I will only consider deformations that allow you to construct a conformal field theory out of another conformal field theory. So not only will we get a new quantum field theory, but the quantum field theory that we get by this deformation will also be a conformal field theory. So these are called marginal deformations. And then Andrea will tell you how to go outside this restriction, and he will describe relevant and even irrelevant deformations. So the course will be structured more or less like this. I will give you a very brief introduction, and it will be very non-rigorous. But in this introduction, I would like to connect these ideas to formulation of quantum field theory that is maybe a little bit more standard, that maybe is what you learn in your first courses on quantum field theory, with a Lagrangian, Feynman diagrams, and all that. But of course, we want to get rid of this restriction as quickly as possible and do things as abstractly as we can. And then I will introduce conformal perturbation theory. I will specialize to conformal theories and explain how to do conformal perturbation theory for marginal operators. And we will see that this is a very rich and subtle subject already, and a lot of interesting things will emerge. And then for the last part, which will be probably tomorrow, there is a bit of freedom in what to do. And I was thinking that maybe I will give you, I will connect the discussion of today to a very old idea of Berry. And it's the idea of adiabatic evolution in quantum systems. And we see that many of the things that we talk about today can be understood, at least partially, in this old language of a standard perturbation theory in quantum mechanics. And then I will briefly tell you how this formalism can be applied. This is a formalism that has found really numerous applications, both in 2 dimensions and in 4 dimensions. And we see how much time we get. And I will be very, very hand-wavy, especially in the last part. So, okay, let's start. And as I promised, I will first talk about quantum field theories in the usual way with a Lagrangian. So let's imagine that we are given a Lagrangian that describes a quantum field theory. And the rules of the game that are told to you when you first study quantum field theory is that you have to look at this and try to find a way to quantize. For example, with a path integral or something else. But you also know that when you encounter these Lagrangians, they do not come in isolation. They often come in families. You find parameters in these Lagrangians, or coupling constants. And so I will collectively denote my parameters as lambda. And just to give you a few examples of possible lambdas, you have the lambda phi to the 4th interaction in 4 dimensions, where inspiration for this symbol. But it could be like a Yamis coupling constant in a gauge theory, or maybe even mass parameters. And you will see even irrelevant parameters can be understood in this way. Andrea will talk about a specific irrelevant deformation called TT bar. And all these things will be, for me, part of the collection of these coupling constants, at least in this initial discussion. And we will soon specialize the allowed coupling constants. So now we'll do something outrageous, and I hope you will allow me to do it with the promise that things will be fixed soon. So we'll draw something. we'll draw some space. And I imagine that this is my space of parameters. So I'm treating these lambdas as some coordinates, so some numbers. And this is supposed to represent the space of my coupling constants. So the idea is that each point here corresponds to a different theory. So you have a theory here, a theory there, and so on. And we will see soon why this makes sense. So you might be very worried that I'm treating these things as numbers, right? Because you know that when you do quantum, even if these are dimensionless parameters in the original Lagrangian, you have issues like dimensional transmutation and coupling constants runs, so you have scales that pop up everywhere. And so you just have to bear with me, and I promise that everything will be made more precise. But even if we ignore this, when we do standard quantum field theory, maybe we're interested in this particular theory. Maybe this is our standard model or some interacting theory. But we don't really know how to do computations in this theory. So what do? We do computations in another theory, say a free theory. This is not the theory that we're interested in, but it's where we can do computations. And so we try to deform the free theory, maybe order by order, and move away from this point, and maybe try slowly to reach, hopefully, our theory of interest. That's more or less what we have in mind when we do perturbation theory. But notice that this is a very subtle operation. And the reason is that we are expressing the observables of the interacting theory in terms of the observables of the free theory. So this is something that we should be very careful about. And this is because imagine that you have a way to describe directly 2 points. This is very common in holography, like in ADS CFT. And in holographic applications, you typically have direct access to a free point, like with standard perturbation theory, and to a strongly interacting point. And still, you would like to compare the two. You would like to see how things change with the coupling constant. So maybe you have a correlation function of local operators. And you would like to understand the coupling constant dependence of this correlation function. I write this. And when you do holography, you want, for example, to test the duality. So maybe you want to compare quantities that do not change in some sense as we change the coupling constants, or protected quantities. So you would like to find things such that the derivative with respect to the coupling constants is 0. But clearly, this statement is a little bit fishy, because the operators that appear here are operators that live in different theories. So when we write things like that, we are forgetting that the operators themselves carry some lambda dependence. Or if you want, they are not really fixed operators. They are sections of your space of parameters. So the appropriate statement would be that there is some connection in our space of operators. And this would be the covariant form of such a statement. That's the only thing that could possibly make sense. Because you see, this, if I do a coupling constant dependent redefinition of my basis of operators, this will clearly pollute this derivative. As usual, when you do differential geometry and you want to compare vectors at different points in the manifold, you have to find a way to connect the different spaces. And what I want to convince you is that you have to deal with this issue in quantum field theory in general. And I will do it by showing you that, in general, this connection will not commute. Okay, so that will be my goal. Any questions so far?
Can we see this, say, at the level of the currency multiplication?
Can you see this?
At the level of the currency multiplication.
Ah, can you see this at the level of currency-Manzik equations, is the question. Well, probably yes, but the currency-Manzik equations are about running couplings. And the discussion in that case is even more complicated than what I will show you. So what I will show you is that you have to worry about this phenomenon already for marginal couplings. And this would suggest that in the case of running couplings, this is even more complicated. There will be even more subtleties. So more questions at this point? Okay, so I have a few issues to sort out here. The most pressing issue is that I'm treating these parameters as just numbers. And I will solve this by only talking about exactly marginal operators. So first of all, I restrict my attention to CFTs, probably in 2 dimensions, since this is a course on 2-dimensional CFTs. And I will remind you that CFTs are completely characterized by giving you a spectrum of local operators. Unfortunately, I will change the notation, but I will explain exactly how the notation changes compared to the course of Sylvain and Lawrence. And my local operators will be denoted by phi I. The I is an index that runs through all the possible operators. I think Sylvain used V of delta for such local operators. And you were taught that these operators are characterized by the conformal dimensions. So there are 2. There are the conformal dimensions of the left Virasoro algebra and the conformal dimension of the right Virasoro algebra. And I will have to consider all the time the sum and the difference of these 2 things. And you will see in a moment why. So I will I will a bit abuse the notation, and I will just call the sum as delta. And so let me put here like Sylvain, Lawrence index to remember that this is not what I'm going to use. And this is not nice to change the notation of U in such a way, but it's really useful for me. So I hope you can forgive me. And also, this is a much more standard notation in higher dimensions. And everything that I say here will carry over to higher dimensions. So just remember, my delta is just the sum of left and right conformal dimensions. And the spin, so I put an index I here, and the spin will just be the difference, the conformal spin. This is better. And a theory is specified if I give you the spectrum of operators, I give you all the conformal dimensions and spins, but I also have to give you the dynamical content. I have to specify the structure constants or the OP coefficients. And of course, this data must satisfy consistency relations. You have crossing symmetry, maybe modular invariance if you're interested in other Riemann surfaces. But in general, this is the content of a CFT is completely specified by this. So I will work with this for now, okay? And our goal will be to understand how you start from a CFT, we want to deform it. We want to find a way to construct another CFT that is in some sense nearby. So imagine that our CFT sits here in a space of parameters. We want to go, first of all, our first task is to go infinitesimally away from it and construct another CFT that will have new coupling new conformal dimensions, new spins, and new structure constants. So I will have to tell you how to compute the variation of these objects here. Okay? Why don't I write the delta of spin? Is it obvious to everyone? So the spin, at least in the theories that I'm considering, is discrete. So it cannot vary continuously with the coupling constants. So I'm just keeping it fixed. So let's go back to the language of Lagrangians, just to have something clear in our mind how to do this. So if we had a Lagrangian, what would it mean to change the parameters infinitesimally? Well, it would just mean that to your Lagrangian, you add some operator. The operator that multiplies the coupling constant, if you want. Right? And we want to understand how to translate this into this language. And more specifically, well, actually, we will not directly work with these objects, even though it's a very convenient and compact way to characterize our CFTs. It's better to work directly with correlation functions to understand how this operation works. So you know that if you know this, you know all the correlation functions. So we imagine that we have correlation functions. I will write them like this. And we want to find an operation that corresponds to deforming our correlation function. Okay? So I will write to you a proposal for such a rule that allows me to deform the correlation function, and you tell me if this makes sense to you. So I will write, this is given by an integrated correlation function of this form. And I left the space for a normalization factor that will be convenient for me, but you can choose whatever you want. And is it clear to everyone why I would choose such a rule for the deformation? Well, first of all, can you read it? Did I write it big enough? So maybe let me describe it if people in the back don't read it. So this is an integral. So I'm deforming well, I don't necessarily have a Lagrangian, but I have an operator, and I want to deform my theory by this operator. And I want to interpret this as an infinitesimal change of the coupling constant that multiplies this operator. And I'm telling you that the rule that deforms the correlator is that I need to insert this operator inside the correlation function and integrate it over the entire space-time. Well, in this case, it's Euclidean, so entire space.
Is the minus sign important?
Okay, so one question is, why did I put a minus sign? And the reason why I put a minus sign is that, and I will also tell you where this rule comes, in case it's not clear. So the idea here is that maybe you have some path integral formulation, where you have some fundamental fields, and you have your action here. And in Euclidean, it has a minus. So when I deform by this operator, I will have to, since this is an action, I will have to integrate the operator. And this corresponds to the deformation of the action, and it comes also with a minus sign. So when I bring it back inside correlation functions, it will give me a minus. But this is just a convenient choice, choosing the minus, just to match what we would get in standard perturbation theory. Also, the 2 pi would be here, and this another convenient thing. Of course, if I put here a plus, it would just be a redefinition of what I call lambda. Okay. So, sure.
Should I worry about what happens when this y comes close to one of these x's?
Right. So this question anticipates the next thing that I need to worry about. So let me hope I wrote everything that I need. So the question is, don't I need to worry about the points where the variable y sits on top of the other insertions in this correlation function? And of course you do need to worry about that. And that's our almost our next question. But even before we ask this, remember that I want to take a CFT and get correlators of another CFT. And if you look at that expression, even ignoring these possible divergencies, it's not at all clear that the left-hand side will behave as a correlator of a CFT. It really doesn't transform correctly for a generic operator OI. So your first exercise would be to derive the first restriction on this operator I, which is that its conformal dimension needs to be equal to 2, and its spin needs to be equal to 0 for that expression to even have a chance of defining a correlator of a conformal field theory. So this will be our first marginality requirement for our operators. And now we have to worry about the problem that was anticipated, the problem of possible divergences in that expression that I wrote. And why do we have this problem? Well, the reason is that it's true that the data that I gave you allows you to compute all correlation functions of the theory. But it allows you to compute correlation functions only at separate points. It doesn't tell you what happens when two operators sit on top of each other. And even for free theory realizations, you had to find some rule to remove these divergences. Normal order, or the normal order prescription was given in the previous lectures. Yeah. I will explain. So the question is, what happens when X and Y collide? I'm going to explain precisely this right now.
Should I modify O?
No, so I will not. So the question is, will I solve this problem by modifying O? And no, I will solve this problem by changing the domain of integration. And
what I require is that your conformal dimension and the conformal difference is to 0. That's
yeah.
all you require at the moment.
At the moment, yeah. So the question is, are you only requiring these two conditions? At the moment, yes, but we will see soon that there are more conditions for marginality. This is not enough by any stretch of the imagination. So let's look at this integrated correlator. So let's first look at, I write again the integral. X1, let's only keep one operator. And so I was saying that the rules of conformal field theory allow me to compute any correlator as long as the points are non-coincident. And I have to worry what happens when Y approaches, say, X1. So in this case, I can use an OP expansion, say that Y is very close to X. Well, let me write X. And you know, when the two are very close, you can just expand this in an OP. And so this would be a sum over all operators of the theory. And now, let me introduce this notation here. So you will see the value of changing variables for the conformal dimension. So the difference between the 2 points is a complex number, and I just separate it into the absolute value and the phase. So this will just be R. So the dimension of the marginal operator, we fix it to be 2. You have the dimension of the operator phi I, and then you have to subtract the dimension of phi j, and then you have a phase that behaves exactly in the same way. Okay? So this is the usual form of the operator product expansion. I just wrote it in radial variables for convenience. And now you can see what's going on, right? If you have two cases, if delta J is greater than delta I, so you have to integrate this over 2 dimensions, right? So you, well, okay, I shouldn't explain this. If delta J is greater than delta I, there are no singularities. This is a completely regular interval. If delta J, so regular. If delta J equals delta I, you get a logarithmic singularity. And if delta J is greater than delta I, smaller than delta I, you get a power law singularity. You agree?
So could you do the calculation for the regular case and then analytically continue in the conformal dimension?
Yeah, so the question is, can I do this computation that I'm doing in the regular case? So I consider only, I imagine that I analytically continue the dimension of my operators so that I get only regular singularities, and then I get the answer by just analytically continuing back to the case or the physical case. And yeah, probably this you could do. This would be a regularization prescription for your interval. As far as I'm aware, this particular thing has not been attempted. I know that some people more recently attempted to continue the dimension of the marginal operator itself, which is the same idea. And, but we will do something different. We will do something that is a little bit more standard. And yeah, so now you have a bit of freedom how to regulate this interval. And I will give you a specific prescription for it. And we will worry about skin dependence and other things later. So the prescription that I will give you to make this interval finite. So let me reinstate the interval here. Is to just, so let me maybe draw the idea. So this is the y plane, and you have these insertions here, the various x's. You have x1, x2, etc. And I'm going to remove small disks around these points, and I excise them from my integration domain. This is my regularization prescription. So I just restrict my interval to the region where this is bigger than epsilon. I cut size balls of size epsilon. Disks in this case. This is a very brutal thing to do to our interval because, of course, I introduce a scale here. Epsilon itself is a dimension length object. So I have broken conformal invariance. And as usual in quantum field theory, you have to do both regularization or renormalization. So now I have to figure out how to remove this regulator and recover conformality, hopefully, at the end of the day. So let me maybe, I don't know if, can you see this far to the left? Let me call this operation. So this is something that I want to deform. So I have my correlator, let me call it G, and put a apex n to indicate that it's an endpoint function. And this operation has defined for me a regularized infinitesimal change of my correlator. So I put reg, R-E-G, here for delta. And now it's important to notice that this object does depend on epsilon. So I will give you my renormalization prescription. So I will, first of all, claim that this object has an expansion in powers of epsilon. So the claim is that this is some coefficient where alpha log epsilon plus so what did I write? I expanded this regularized correlation function in powers of epsilon. So I had inverse powers corresponding to the power law divergences. I had possible logarithmic singularities if I have operators in the spectrum, degeneracies, or even the operator itself popping up in the OP. And then I have a finite piece, which I conveniently called delta ren from renormalized of G of n. And then I have terms that vanish with epsilon. And as you might expect, I identify this object here as my prescription for the renormalized correlator. So this is the rule that I give you. And now you might worry. You might worry about many things. You might worry about the conformal invariance of this correlator. You might worry about skin dependence of this operation. You might ask, well, what if you had removed singularities in a different way, with balls of different radius, or with maybe an analytic continuation operation, or even other things? And this is another worry that is legitimate. And I will not fully answer these questions. And let me just tell you that in 2 dimensions, this can be solved, but it requires a little bit of a more abstract approach to conformal field theory in terms of Riemann surfacing and Sewing relations. So I will not have the time. But instead, I will try to convince you that this particular regularization prescription makes sense and makes physical sense. So that's the route that I will take. Yes, question. Yeah.
And then maybe losing my mind, if I just call epsilon to epsilon,
yeah,
don't I get some ambiguity already?
Yeah.
This very simple thing.
Mm-hmm. So the question is, well, the first was, this is positive, of course. The second is, what if I, instead of using balls of size epsilon, I use balls of size 2 epsilon? Well, you should immediately see that this part is fine, so no worries about that. Then you have a logarithmic piece. This log of 2, this infects the finite part of the correlator. The question is, will this change give me a correlator that is the same correlator, just with a maybe calculating in a different point, or will it give me the correlator of a different theory? And the answer is that it gives you the same correlator, and I will not be able to prove it to you, but I encourage you to do it in the exercise session. So I encourage you to do this particular exercise for 2-point functions. And you can ask yourself, okay, you can do this for 2-point functions, and do this and expand it, and then you can look at the logarithmic piece and try to change the logarithm and see what ambiguity this gives you for the finite piece. And you will discover that this is a completely benign ambiguity. Maybe I will say something more in a few minutes about this. And in any case, we can discuss this in the tutorial session for this particular example. All right, so I gave you this prescription for my renormalized correlator. And now let me explore a little bit what it means. So we want to understand the meaning. We want to see if we can understand the meaning of this operation in that geometric language. So let me do the following thing. First of all, let me look at the marginal operators themselves. So I defined my deformation in terms of these operators. And now let's ask ourselves, what if I had used different coordinates? What if I change the definition of my lambda i's? So imagine that this corresponds to some space of parameters. And instead of using lambda, I use like lambda prime of I, some function of the lambda, just a change of coordinates. And let's see what this looks like in these new coordinates. So I can just, so this will be some lambda prime I with some new operators, O prime. And I can just see how the delta transforms, right? So this is just d lambda I, d f j, d lambda I, O prime j, right? And yeah, I screwed up the indices. Right? So this is j, I. Right? So we see that the new operators are related to the old ones by the inverse, by the inverse transformation, the inverse Jacobian of the of my change of variables. That means that this particular object transforms as a basis of tangent vectors under changes of coordinates. This really transforms like the basis in a coordinate basis, the basis of tangent vectors associated to the partial derivatives. And so you might expect that this operation that I defined here you might expect that this should be interpreted as some sort of derivative. So let me put a question mark here. Right? This is a natural guess because this object here transforms as a derivative operator, and it corresponds to a change of this correlator with respect to the parameters. So maybe it's clearer if I write this as explicitly. This I mean the partial derivative with respect to the parameter lambda I. And we will soon see that this is not correct. This interpretation cannot possibly be correct. And why is that? So first of all, let me simplify notation a bit. Let me define this. Let me define this as, okay, this is a bad idea. Let me define this symbol here. Okay. And let's look at what happens when I do two such deformations. And of course, I will do the deformation in the reversed order.
So, Marta, just to make sure that I understand. On the left-hand side of the equation above,
yeah,
you have the complicated operation that you described.
Yes.
These balls and so on. On the right-hand side, you just mean the ordinary differential equation of some function that depends on certain parameters.
Right. So the question is, what do I mean with the left-hand side and the right-hand side? So I will. So the left-hand side is indeed defined in this way. I just take my integrated correlator, and sorry, of course I should have written renormalize. This is the issue. Yeah. And there is no epsilon dependence, of course. Thanks a lot. So the object on the left-hand side is defined, well, the object on the left-hand side is defined through this procedure. You do your integrated correlator, you cut little disks of size epsilon, you remove the divergences in epsilon, you keep the finite piece. The right-hand side is not defined with what I told you. I'm just asking imagine that we have already solved the theory for every value of this would-be parameter, lambda. And we have all the correlators as a function of lambda. If I have all the correlators as a function of lambda, then I can surely take the normal derivative as a function, right? And I'm asking whether this operation that I'm defining very explicitly can possibly be interpreted as doing this. That's all that I'm asking. And what I want to argue is that this is not quite correct. And the reason is that if I do this thing twice, and then I do it in the reverse order, I will show you that this is, in general, not 0. So what does it mean? It means that whatever operation we are doing, this can't really be interpreted as a standard derivative, but it should be thought of as a connection, or okay, a covariant derivative in this language. And the reason you can probably anticipate here, because even though I kind of hid the dependence on these labels y, I1, I2, etc., from my definition of G, they are still implicitly there. You should really think of this as carrying indices, I1, In here. And this connection will tell you how to handle this index dependence. So it's like really taking the derivative of a tensor as opposed to just a function. And let's see. So I think this is a good time to take a break because then I can describe in detail how to do this operation in quantitative way. And questions, of course, are welcome. Yeah, sorry.
You were worried about similarities, but I think we can speak about the simplest similarity, which is what if infinite volume, one line goes to infinity.
So the comment is, I only talked about short distance singularities when y is close to x1, x2. Why don't I worry about long distance singularities since I'm iterating over an infinite volume? This is what you're asking me. And I'm sorry, I should have told you, indeed. There is a, I should have told you, but I didn't, reminded you that this correlator, with whatever insertion, goes to 0 at infinity at least as fast as 1 over y to the 4th. And this you should be able to prove with what you learned in the previous courses. And, but it's not such a crazy claim, right? Because you can imagine that whatever is here, I keep doing OPE expansions, etc., right? And when this is very far, the only contribution that can possibly contribute to this kind of approximate two-point function is the operator itself, or an operator of the same conformal dimension. So this is why, at large distances, this is the behavior of a correlator. And this is really what you also use implicitly when you put correlators at infinity, when you put certain operators at the point at infinity. You only multiply it by a factor of y to the 2 delta to make it finite. So you're implicitly using the fact that the correlators at large distances decay at least as fast as this. Yeah.
I understand the argument if the operator was not marginal, you would have problems.
Right. So the comment, if the operator was not marginal, you might have problems. Yes, if the dimension was smaller, you would certainly, no, bigger. What is it? Smaller, yeah. You would definitely have problems. In particular, if the dimension is 1, I guess you would have a logarithmic singularity at infinity. Yeah, I don't know what that would mean. That would be an issue if you want to deform the theory by a relevant operator. Maybe you will encounter such issues. Yeah. I don't know.
More questions? If not, let's thank Mark again.